All right, there we go. Didn't have my mic plugged in and I realized it, thankfully. Welcome back, Math 154, our next to last class, believe it or not. So today's the 29th. We got some homework due today, 6.2. We got some homework due next Wednesday, 8.1 and 8.3. Get those done sooner than later since you'll probably be needing to focus on studying for the final closer to that date. The next Excel, I mean, you should start studying now, of course. And this will be our last Excel. That's 9.2 mutual fund. Remember your formula sheets that you're allowed to use, formula sheet that you're allowed to use for the final exam is in Canvas. It's in the reviews section. The final is going to be 1 day only and 1 attempt. I am not allowed to give multiple attempts on a final exam. I did look into it. And that's going to be Wednesday the 6th. There will be no class on Wednesday the 6th. I don't want to hold class on the same day that I'm giving you an exam. I don't think that would be fair. That's not how we normally do things, right? That's why I gave you multiple days for the midterm so that we at least had some more time to talk. And a little more flexibility because I know not everybody can be here for the live lecture. And there goes my dog. So, distractions. The final exam review. So this is going to be in 2 different chunks, and this is how I always do it for this course. You already have the review for the midterm, and most, I would say 60, 70%, maybe even up to 75%, most of the final exam will be coming from midterm material, the first half of the class, because when I say first half, air quote, the midterm really goes about to the first 60% of the material traditionally, but we're really not going to get into chapter 9, so I've got to trim a lot of that out. I skipped a couple of things in, or I'm skipping 1 or 2 things in chapter 8, so I have to cut that out just because of all the complications we've had this semester. We've made the best as we could with this. So again, I'm not going to give you anything new for material from chapters 1 through 4. To study for the final exam material that is included from chapters 1 through 4, go back to your midterm review and go to your midterm. I will say that questions are more likely to be similar to the midterm because that was a much more refined and least amount of questions, but I can still pull a couple of questions from the midterm review. So I will pull from both of those things. I'll pull more questions from the actual midterm than the review, but I will pull from both. And then you'll have maybe, I don't know, 6, 7 questions, somewhere in that ballpark, probably 6, that will come from chapters 5, 6, and 8, and maybe something in terms of chapter 9 without getting super complicated with it. Because there's still some stuff that I could do that's chapter 9 based, but you already know the math on it. So we're not going to get to everything that's on that formula sheet. We're not going to get into mortgage payment and car payment formula, that the biggest ones at the very bottom. We're not going to get into a couple of the more complicated ones as well, like annuities. We're going to get to talk about them very briefly on Monday, but I would rather you understand what a mortgage payment looks like, what an annuity looks like, then here's the big kooky crazy formula, inject numbers into it. Those are both awesome things to be able to do, but I'd rather you get a more basic understanding. That way, 5 years from now, when you clearly will have forgotten the formula, you can go, oh, well, Mr. Beckner showed me this website and I can really quickly calculate my mortgage, or how much I should put away to have $1 million later, or whatever it might be. Because this is supposed to be a practical math class. The first half is all about ratios and percents, because ratios and percents dictate a lot of our lives. And you can do a lot of things in the real world using those concepts. You can understand data better using those concepts. You can make better decisions based on those concepts. The last thing I want to rant about, your final grades. Remember that you are defaulting to a pass or withdraw, which is failing but doesn't hurt your GPA situation. So automatically, if you do nothing, you're going to get a passing or fail, or again, a W, which is a quote failing grade. Just doesn't have a GPA effect. It means you have to take the class again. If you want an A, B, C, D, or F specifically, and you don't get to request which one, I mean the one that you earned, you have to submit that form. They sent you an email with a link, and I think the form is in Canvas. I gave you an email pointing out all these details. I do not have the exact date off the top of, I don't even say off the top of my head. I don't have the exact date for when you have to turn those in. I have had a student tell me that it was the 10th. I've had teachers tell me it was the 7th or 8th based on whether it was a 12-week or 16-week course. So what happens when someone's presented with different information? You do your research before you make a conclusion that it's the 7th or 8th or the 10th. So I don't know what it is right now because I've been told two different things. I am hoping, and my fingers are crossed right now, I know you can't see it, but I'm hoping that by Monday I will have that. So you need to think about now, how have I been doing in the class? Do I think I'm going to come out with an A or a B? If so, I would probably take the A or B instead of just a passing grade. That way I get that GPA boost. If you think you're walking out of here with an F, don't get the A, B, C, D grade. If you think you're walking out of here with a D, that's up to you. I would probably take the pass-fail grade personally, but that's me personally. I can't tell you what to do, but a D would typically hurt your GPA. If you're a student, like I said, you made an A or a B or a C on the midterm, you did your project, you've been doing your homeworks, everything has been flowing like it should. If I were that student, I'd take the A or B grade. If I was the student who hasn't been doing anything, who hasn't been studying, who has been hit hard with this situation and can't always get to their technology, or has family issues, anything like that, maybe I'd take the pass-fail option. Again, fail being a W, not an actual F. You still retake the class, but you don't get your GPA hurt. If you email me and tell me, hey, Mr. Beckner, I want the ABC grade, it doesn't matter. I'm not going based on that. I am only going based on the official survey that you have to fill out. Now, if you don't fill it out, again, by default, it's the pass, which is a P plus or P minus, or a fail, which is a W. If you fill it out and choose the ABC grade, then I'll give you that instead. Okay, so rants aside, I had thought about doing one more simple quiz, but I'm not gonna. I definitely didn't want to do another Excel homework. We did not do nearly as many Excel homeworks as usual. I don't want to say nearly. We should have done like 3 more, maybe 2 more, probably 3 more. But we had complications. There's a lot to cover in this course, a lot of weird stuff. So we made the best of the situation. Hopefully you come out of this with a better understanding of some concepts. All right, back to the chapter notes. So today we're covering 8.3 in chapter 8. And then maybe we'll talk about chapter 9 a little bit. And chapter 8 focuses, sorry, I just hit my mic, on what we call the correlation coefficient, and also an effect of that, the coefficient of linear determination. So we saw a letter previously when we were doing some Excel stuff, when we had some data points that we plotted, and then we did a line of best fit, or a curve of best fit, an exponential curve. Then I displayed the R squared. That's what R squared is. R squared is the coefficient of linear determination. And that's this big fancy sounding set of words. It just basically says how well the data fits the model. That's what R squared is. R and R squared are related to each other in the fact that if you have R, if you square it, you get R squared. Or if you add R squared, you could take the square root, something we don't really do too often in here, but you could, to get R. Now, because of the way numbers work, when you square something, a negative becomes a positive. R can be between -1 and 1. That's the bounds for a value of R. It can't be -2, it can't be +3, it can't be 1.01. R is strictly between -1 and 1 for reasons, and those reasons have to do with R squared. So R squared would have to be between 0 and 1. So if you wanted to see this written out as an inequality, -1 is less than or equal to R is less than or equal to 1. But if we're talking R squared, 0 is less than or equal to R squared is less than or equal to 1. R being the correlation coefficient, R squared being the coefficient of linear determination. Quite honestly, you don't need to have those names memorized moving forward. You just need to understand what R squared means. That's what I want you to take away. Maybe your teacher has actually called them the wrong names every now and then, called them names backwards. Maybe he has, maybe he hasn't. I don't want to say that officially in recording, but I think you can get what I'm saying there. The name doesn't matter. It's understanding what the value is and its effect. So we can talk about whether the data fits well or not based on R and R squared, but admittedly, it's better to base it off of R squared because of its relationship we'll see soon. So if R was -1, that's a strong negative correlation. So what would that look like? You got data points, and let me just do it all positive axis. So here's some data, dot, 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 dot. And then they make a line of best fit for us, Excel does, that is. And it goes pretty much through all the data, really, really, really close. This R value would probably be about, I don't know, -0.89, let's say 0.9. And this is an approximate. This would be a strong negative correlation. It's pretty close to -1. -0.9 is really, really close to -1. The negative correlation means the slope is negative. So as one thing increases, the other thing decreases, and it's strong because the line is close to the data. What about strong positive correlation? Well, here's some data points. Oh, wow, I got really all over the place there. We do this. This is what the line of best fit Excel would give us. It would probably look something like that. And this R is probably about 0.85. Again, I'm really guessing these. It's a strong guess. It's a positive correlation because the slope is positive. No correlation means that the data is just kind of all over the place and there's no real reason that the line has to look like it. So here's a bunch of data that just seems like it's all over the place, and maybe Excel makes this as your line of best fit. It's pretty flat. So Excel's saying there's a positive relationship, but this is definitely a weak value. This R is probably pretty close to 0, like 0.15 maybe. So that would be close to no correlation at all. Now R is okay, but R squared is better to use because of its relationship as a percent down here, which we'll talk about in a few minutes. And Excel does not give you R, it gives you R squared. Let's show you one more time how to get that. So let's just say we had some X and Y values. Go down, please. The X values of 0, 1, 2, 3, 4, 5, 6, and Y values of, let's go with, I don't know, 10, 12, 15, 17, 23, and 27. Oh, there's another one. Let's go with 34. So if I highlight that, we insert our scatter chart. We get this. If we then go to add chart element, trendline linear, that's not too bad. I mean, this one's a little off, but the rest of them are pretty good. Add chart element, trendline, more trendline options. That little side menu opens up. We can display the equation with the slope and the intercept, so we could use interpretations that way. But then this other bottom button, display R squared value. So the R squared for this is 0.957. So you can see that's pretty close to 1, and you can see that these points are pretty close. Let's do another one. Let's go 0, 1, 2, 3, 4, 5, 6. And let's go 1, 12, 3, 90. Oh, no, that's going to be too big. Let's go with 37, 10, 6, 12. So let's make a chart out of this. Same thing, insert, scatter chart. This guy is way off. Then let's add chart element, trend line, linear. So that one's, again, way off. Add chart element, Trendline, more options. Oh, that's right, I have to close this menu first. It's kind of a silly thing. Trendline, more options. Display equation, display r squared. Look at that r squared. Can you see that? It says 0.03. That says that's a terrible fit. And it's mainly because of that point, I feel like, but the rest of them don't really seem, it goes up and then down, up, down, up, down. It just doesn't seem to be a really good fit. So that's why the r squared is so bad. I actually would have predicted the r squared to be like 0.1 or 0.2, not as dramatic as that is. But again, I mean, when I predict it, I'm just throwing numbers out there. So r squared, the closer it is to 0, there's a weak or no correlation. So that's still true. But there is no -1 aspect. It only goes between 0 and 1. So 1 is a strong, if it's exactly 1, that's perfect. But the closer it is to 1, it's a stronger correlation. So with r squared, you can't tell whether it's a positive or negative correlation. So you can't tell the slope, which is the positive or negative correlation. But it gives you a better numerical idea of the actual correlation. And in fact, it tends to be more extreme numbers. It typically tends to float around close to the 0 or close to the 1. You don't see as many in like the 0.5 range as you might for an R. And that's because when you square a decimal, it tends to shoot to 0 or 1 a lot quicker. So some data, why did it do that? If we had some data that looks like this, I didn't mean to have that little bump. And then it gave us our line of best fit. I'll do it in black for emphasis. This thing is dang near perfect. That r squared was probably about 0.96. But if we had data that was like this, it seems like the dots are kind of going up and right. It seems like they're trending this way. So the line of best fit Excel would give us is probably going to look like this, kind of sandwiched between the points. But because there's all these points much further from that line, that r squared is probably something like a point, I don't know, 0.4. Okay, the good thing without actually using numbers is you can't prove them wrong. So again, with the r squared, you can't tell that it's a positive or negative correlation, but you can still tell how well it fits the data. You have to use your eyes to tell whether it's positive or negative correlation. So the first one I drew would be a negative correlation, which says the r would be closer to -1, whereas this one, that's a positive correlation because the slope is up and right. So that r would be in the positive range, maybe 0.6, 0.7 in fact, because if you square one of those numbers, it puts you closer to 0.4. Squaring 0.6 gives you 0.36, squaring 0.7 gives you 0.49. So what is this actual relationship with r squared? Why is it more important? What do we get to take away from it? Why do we use it instead of r? Because if you take the value of r squared and you convert it to a percent, which means multiply it by 100 or move the decimal right twice, it gives you the direct percent of correlation. R does not, r squared does. So r squared gives us a percent correlation. And you get this kind of fancy sentence like you do, kind of like with slopes and intercepts that you need to kind of use over and over and over to understand. So again, where I have r squared times 100%, this right here, that's just the percent. That's r squared converted to a percent. This right here is just r squared as a percent. That's what the highlighted thing is. So the sentence is, the percent of the variability in the output can be attributed to the variability in the input. In other words, it seems like the input changing correlates to the output changing as this much percentage. So if it's a perfect correlation, then it would be 100%. If it's kind of crappy, maybe 10% or 20%. So the R squared gives you a percentage of how much the output seems to correlate with the input. Now, correlation does not demand causation. We talked about that extensively last class. Just because you have perfect correlation does not mean that one thing caused the other. You would have to go into the real world, into science and engineering, to actually prove that in some manner that it does correlate. I mean, that it does, excuse me, show causation. Correlation does not imply causation. It's a good sign of causation often, but not always. Kind of like how we talked about pirates versus global warming. There's a pretty good correlation between those sets of data, but in terms of causation, not so much. We saw a problem involving butter and divorce rates in, what was it, Maine or some state in New England at least. And in fact, we have a worksheet for that that we can just kind of eyeball for a second. Where was it? Maybe it's only, I think I have a newer edition in paper. Where are you? Maybe it's lower. I know I saw it. Where'd it go? Well, that's frustrating. I was literally looking at this earlier and now I can't find it. Okay, that's all right. We'll use another example. I scrolled past it. There it is. Here it is. Here it is. So we in passing talked about, okay, well, there seems to be some correlation between consumption of margarine and divorce rates in the state of Maine. I had it right. And if you actually plotted the consumption of margarine in pounds per person every year versus the divorce rate every year in that state, you end up with this. So when we had 4.1 roughly divorces per 1,000 people, they were consuming about 4 pounds on average per person. When we had 5 divorces per 1,000 people, they were consuming about 8 pounds per person. And when you get Excel to make your line of best fit and show the equation, show the R squared, look at that R squared. Look how well these points fit the line. I mean, it's almost perfect. And that R squared being 0.99 roughly says that that is almost a perfect correlation. So there is an extremely fascinating correlation between divorce rates and margarine consumption. But there is no logical reason for one to be causing the other, for one to affect the other. Now, what you might get is some scientists saying, well, margarine does all these things to the body. Instead of eating butter, people are eating margarine, and maybe margarine's bad for you, and maybe it's making people crankier, and maybe that makes them divorce. Maybe they have the inputs and the outputs wrong here, in my opinion. So that's what some scientists could do to try and show causation. But right now, all we have is correlation. This does not say one is causing the other. It just says that for some reason, this data is correlating nearly perfect. And again, we don't focus in this course on how to prove causation. That would be, graduate school for us, and science and all sorts of things, medicine, whatever, depending on the topic. All right. Back to the notes because I had 1 or 2 more things to say. Nope, that's not our notes. This is our notes. Outliers. Data points that seem to not match very well. These are what we call outliers. oddballs, screwballs, really weird data that just doesn't fit with everything else. Outliers are usually just a couple of points. They can be, more than a couple, but if you've got, say, 100 data points and the everything seems to fit really well except for one or two, those one or two are often called outliers. Now in statistics, often what people will do is they'll throw away the outliers for their data. They'll say, all right, well, everything fits really well except for these couple people, so ignore them. And now everything fits perfectly or near perfectly. But that's the thing about the real world, you very often come up with these outliers. So outliers are data points that don't seem to match with everything else really well. So everything seems to have a really good fit, and then you got these one or two or three oddballs that are just way outside the norm, kind of like your math teacher. Haha, jokes are funny. So we call them outliers. Now, are outliers always thrown away? No. A lot of people say the outliers are important to understand that not everything fits perfectly, but sometimes people like to manipulate data and throw away the outliers. When we talk about median salaries for Americans, a lot of statistics will eliminate like the top 100 richest people in the world because they're outliers. They make such a ridiculously large amount of money that they throw off the averages, whether you're calling it a median or the traditional average, a mean. They don't really affect the median, but they would affect the mean. So you'll throw out the top 30 or 50 or 100 people, whatever, some number of the wealthiest, because when you include them in an average, it goes from, all right, the average American makes $30,000 to the average American makes $70,000. Because they make billions and billions of dollars, it throws off everything else. It's not good for the actual data. They're very, 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 very special cases, and not even just the 1%ers, the 0.00001%ers. Back to the worksheet. Where's the other one I wanted to show? So this right here, this is a graph of perfect correlation. So having to do with the miles from Albany versus the toll. So this toll has something directly to do with how far away you are from Albany, how much you're going to pay on the toll. So a toll road based on the distance. And you can see that when they did their data points and Excel gave them a line of best fit, R squared was 1. That was a perfect fit. Again, we saw the margarine one that this was near perfect because R squared was 0.98. We have this oil price per barrel. And what they ask us to do is sketch a linear trend line and estimate the equation. I'm going to skip the estimating the equation part, but let's just try and do a trend line for it. Now, again, this is not something you're going to get tested on. I can't test you on physically drawing a line since it's a digital test, so don't sweat this too much, but it's something to take away. You're just trying to draw a line that, I'm doing this just as a guess. So you want to make it so it looks like all the data points are kind of sandwiched between your line. And the more scattered the data is, the tougher this is. So I would think it probably looks something like, let me use my phone. Let's see if I do here. I'm just trying to get a good setup. And I want it here. Okay. Let me hit undo several times. Is that going to be good? That's not too bad. A little low on the left. Let's try that again. There we go. And I shouldn't go that far over. I don't want to go into the negative side. There we go. So that's just me visually spitballing this, eyeballing it, and saying, okay, I think that looks pretty good because the line is pretty close to the points. I don't have any that are too crazy far off. And again, if I had data that was far off, I wouldn't be able to match that data. I'd have to, again, just make my best judgment. Those points look pretty good. So if I wanted to guess the R squared, that's probably in the ballpark of 0.9. Maybe 0.92, 0.93, I don't know. Again, I'm just guessing right now. That's all I can do. I would need Excel to tell me that. I I have to clear my screen to scroll, unfortunately. Sorry for that. Then they say to do the interpretation of the slope. We've done that stuff before. We don't have time to do it again, but that's where we say that the price is changing this much for every year, and that the starting value seems to be this much, which would not make sense because we're doing it as a year, not a year since model. Then to predict, you can just plug the year 2020 into this equation, since the model is not based on years since. Let's go to this one though. We want to do this interpreting. So gas versus oil prices. So we talked about how oil price affects gas price, but just because oil is zero, if oil was free, gas would not be free because you have refineries, you got to pay the employees, you got to pay for the materials to refine, you got to pay for the building, you got to pay taxes, and then you got to sell it at a markup to the customer. Also, the gas station's got to take a cut. So that's why even if oil was free, gas wouldn't be free. It's still going to cost you $1.20, somewhere in that ballpark. I don't know, guessing. Interpret the R-squared value using the R-squared percent of the variability of the output can be attributed to the variability of the input. So that's what we want to do here. I'm going to focus on this. They gave us the R-squared. It's 0.9839. So let's pull out annotate. So if R-squared is 0.9839 as a percentage, doesn't matter if you capitalize it or lowercase it, that is 98.39%. That is a great correlation. Terrible looking percent sign. I've gotten spoiled with how Word edits my handwriting. There we go. So what we can say is that, and I'll pull out the text. The first thing you say is that percentage, 98.39. And then you say of the variability of how much it changes in the output. What's the output? Output is the price per gallon of gas, or you could just say gas prices. So 98.39% of the variability of gas prices are due to the variability of, make my window bigger, and then the last part of that sentence, it's attributed to the variability of in the input. In of, same thing. What's the input? The price of oil. And you can say it, you can say oil price fancier, the price per barrel of US oil. And the gas prices, you could say price per gallon of US gas, but saying gas prices and oil prices is good enough for a sentence, right? So there is a very strong correlation. It's almost 99%, 98%. So there is a 98% correlation in this data. This data is not telling us that there's causation. You have to get into the science behind it, the things I was saying earlier, that oil has to be refined. You have to have people doing that. You have to then have gas stations selling it. You've got truckers moving it. I mean, everything is there. But if you bump up oil prices, gas prices are going to bump up with about a 98% correlation. So in other words, if oil prices go up 100%, the gas prices are going to go up about 100% at a 98% efficiency. So 98% of the time, they'd go up 100%. So maybe they don't go up exactly 100%. Maybe it's 102%. Maybe it's 98%. But it'll be ridiculously close unless that data is an outlier, because that 98% correlation says you could have this one really weird oddball where oil prices didn't actually go up, but because of a break in the supply chain, something that the news just loves saying right now that I'm getting sick of hearing, specifically with food. Sorry, real world stuff. there could just be something weird going on, like right now maybe, and even though oil prices don't change, all of a sudden gas goes up to $4 a gallon because we're not going to be able to produce anymore. Again, something really weird. I'm not saying these are facts. I'm giving scenarios that are not happening. So that's why it's not perfect. If this was 100%, then we would expect perfect correlation. So we wouldn't expect any freaky outliers. But anything less than 100% says there can be an outlier. There can be some weird data or several pieces of data, or if you have a terrible R squared down in like the 30%, 40%, you don't even want to call them outliers. It's just the data doesn't fit very well. Let's look at another one of these. Let's clear the drawings, take off sketch. Come on. I hate when that thing goes hiding. There we go. The next one I want to look at, they talk about the strength of schedule with women's Division III basketball. Strength of schedule has to do with Team A playing Team B and how we set it up. The relationship between, like, are we a number 1 seed versus a number 16 seed, or are we a number 5 seed versus a number 6 seed? So the likelihood of a team winning based on their position in terms of wins and losses. So they go through some questions that, once again, not really enough time to talk about. We're doing this just a very brief synopsis of everything. What percentage of variability do you think is due to variability in the strength of schedule? So what do you think the chance of winning a game has? How strong do you think the chance of winning a game based on the strength of schedule is? Do you think it's strong or weak? And a lot of people will say, I think it's pretty strong. We would take 10 minutes in class to discuss this if we had group work still. And I'm trimming the group work down outside of this class again because we're near the end. So I haven't been doing any more discussion boards. But a lot of people instinctively think, oh yeah, if you put a number 1 seed against a number 16 seed, number 1's definitely going to win. If you put a number 5 seed against a number 6 seed, number 5's definitely going to win. I'd be inclined to believe you on the first one, but not so much the second one. 5 versus 6, I mean, maybe the difference there is just one win or loss, and maybe the number 5 team has 3 people out because they got fined or something like that, or they're sick, or whatever. Maybe the number 6 team just got some new idea, and there's all sorts of things that can change. There's lots of dynamics. Just because one team is scaled versus another team does not mean that Team A is better than Team B just because they're 1 seed higher. So yes, it's more often true with a 1 versus a 16 or a 1 versus a 64, but when they get closer to each other, it gets a lot shadier. So a lot of people initially answer, oh yeah, I think it's going to be like 60, 70, 80% strength. But in fact, when you plot the data, their win percent chance against their, and I'm not going to go into what these values mean, what they're calling the strength of schedule as a number between 0 and 1. Let's skip that conversation. But the data points end up being pretty spread. They're kind of clustered and they're moving slightly up and right, but they're not super tight. They're definitely clustered. And Excel gives us our line of best fit, and there's tons of points all over the place, not really that close to the line. And that's why this R squared is pretty trashy. That is a 13.87%. Correlation. So that says that, let's just round it to a near solid, 14% of the variability in the strength of schedule is due to the variability in a win percent, because they plotted the axes, in my opinion, backwards. I honestly think it should be that 14% of the variability of a win percent is due to the variability of strength of schedule. The inputs and the outputs get a little shadier when you start talking about things like this. But again, if we had done this in class, I would expect guesses to be all over the place before we actually saw the chart. But yeah, strength of schedule overall is just, what's your whole season's lineup of difficult plays? How many times are you going against teams higher ranked than you? How many times are you going against teams that are lower ranked than you? which also kind of implies that if you are like the number one team, well, all of your other games, you're going to be facing lower people, so you've got a stronger strength of schedule. If you're a number 64 team, you're going to have a very weak strength of schedule because everyone's higher than you. But again, when you look at every single team in combination, not just the strongest, not just the weakest, there's not a very good correlation. Now, does that mean there's no causation? Again, no. Correlation and causation are two completely different arguments. When we see excellent correlation, that's when we go and try and show causation. If you see crappy correlation, you probably don't want to try and show causation. I am not saying there isn't. I'm saying that you usually don't try, which is also a reason why we may have had some really bad medical advice for a while. And I kind of hinted at that stuff last time. I don't want to get into it this time though, because again, I'm not a professional. I'm not telling you any dietary guidelines. I'm telling you to think for yourself, do your own research, form an opinion. Don't just believe something because you read it once on Facebook. Is there anything else I want to say from this chapter? Sorry, I'm looking through some things. I think that's pretty good. Nope, drop something. Give me about 30 seconds, maybe 60 seconds. My pages were out of order because I was flying through them. All right, let's clear this. Let's go off of annotate. I wanted to show this last one. And then we'll kind of start a brief synopsis of chapter 9. So we got a memory experiment where you're given a string of letters. So in other words, just some letters back to back, and we're told to memorize them. And if we gave you 6 letters like A, Q, R, Z, P, D, 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 it's pretty easy to remember 6 letters back to back. So they found that pretty much 100% of people were able to memorize them. So 6 letters, 100% were able to memorize them. 7 letters, we saw a little drop that looks like maybe 97, 98, 95, somewhere in that ballpark. 8 letters, so B, D, F, Q, R, Z, L, O. That's going to be a little tougher. Each time you add a letter, it gets a little tougher, and then a little tougher, and then a little tougher, and then a little tougher, until it becomes almost impossible for your average person to memorize all 12 or 13 or 14 letters. This is a skill that some people are better with than others. I'm not that great at memorizing letters, but I can memorize numbers all day. I spent an hour studying pi for fun when I was like 22 or 23. I mean, it took me an hour to memorize it to 100 digits, but I'm really good with numbers. If you told me I don't want to say that on video. I was gonna say that, make a Social Security joke, but I'm not gonna make that on video. But you can use your imagination. And again, it was just a joke. But if you told me, say 7, 8, 9, 10, 11 numbers back to back, I can memorize them without really trying, because that's how my brain works. But other people work better with letters. Maybe someone can memorize 12 letters back to back really easily. Also, how your brain's programmed makes it easier for some than others. Is that a necessary skill? No, it's not what I'm saying. It's just a skill that some people have. But you can see that there's a really steep drop off after 9. So 9, it looks like about 60%, so more than half were able to actually achieve that, because they had 5 seconds with it, and they had to wait 10 seconds to say it. But then when you gave that 10th letter, it went from 60% to 20%. That is the biggest drop out of all of them. Now, this is never going to go negative. It's not going to go to negative 10% can do it. At the least, it could be a 0. And if you survey enough people, there's still going to be someone in there that can do it probably at 13, 14, 15 letters. But a small population, it'll probably go to 0% eventually. So it flattens out pretty quick. And if you did a linear fit, it would probably be pretty good. But there is this exponential decay relationship, and we didn't talk about decay too much except for that one time with the decibel problem, the safe listening distance. That exponential growth explodes eventually, exponential decay flattens out to nothing. So this is that flattening out to nothing, because you'll have the 1 or 2 people out of 100 or 1,000 or 1,000,000 that can still do it at 15, 16, 18 letters, maybe even 100 letters, if someone has some crazy, amazing brain. So we had Excel give us an exponential approximation. We display the equation in the R squared, and we can see that it's an 88% fit. And you might not think that this is 88% fit, because look at over here, it's 6. That's way off. We should have a 200%. Well, first of all, that's not even possible. So there's something weird going on there. That's just because the model can't fit all data perfectly. This one's okay. This one's okay. I'm not too happy with these 3 points, but 7, 10, 11, and 12 fit so well. And the way exponential curves kind of consider data, they don't mind a few points being off the curve this far like a linear model does. The linear approximation would hate the fact that these are that far off. But an exponential is okay with just a few what feels like outliers to the model. So that's why this is still a pretty strong fit for exponential. But again, if you had 3 points this far off for a linear model, I'd expect that R squared to be like a 0.8, 0.7 maybe. Again, just guessing. So this says that 88% of the variability in people being able to answer correctly is attributed to the length of string of letters, or the variability in the length of string of letters. Do you have to use the fancy word variability every time? No, you can say change. So the change, or the likelihood of someone being able to answer correctly, has an 88% correlation with the length of the string of letters. So again, you don't have to use fancy words as long as you understand what the sentence means. You can break it down into simpler terms. All right. Where are my chapter 9 notes? I have the chapter 9 notes posted. I'm not going to go over every little detail of this, especially the plugging in into the actual equations. Like I said, I'm going to skip all of the complicated math and just use websites instead. Because 5 years from now, you're not going to use my formulas. You're not going to go to the internet and find the formula. You're going to go to the internet and try and find a website. Or just rely on a professional who might be lying to you. You never know. So chapter 9 is all about finance. This is my favorite chapter. I wish I could do this for half the semester, but we have too many other topics to cover. And unfortunately, we're going to get the least amount of time to talk about it ever because of coronavirus. And the way I approach this chapter is interesting. I don't do it in order. I do it in more of a natural order to your life, because typically in your life, at least your adult life, you tend to acquire debt before you acquire savings. How do we acquire debt? We get car payments. We get student loan debt. We get mortgages. We get credit cards. Now, a car payment, honestly, not the end of the world. A mortgage, not the end of the world. Student debt, I mean, 10 years ago, I would have said not the end of the world. Now it's a lot worse. Thank you, Fannie Mae. Thank you, politicians getting their pockets lined. I love rants, I really do. But a mortgage is actually good debt. A car loan, some people can argue is a type of good debt. Now, that's if you're driving around a $10,000 car, not a $100,000 car, unless you're making $1 million a year. You have to have a proportional car to your salary, a proportionally valued car, at least, again, opinion if you want to be smart financially. Again, this is not me telling you what to do. Live your lives. I just give sound advice. Not advice, education. Remember, not financial advice. Don't sue me. So these mortgages, this is your home loan, whether it's a house or a condo or something else with a similar name. There's lots of different names for those. Typically, these come in 15 or 30 years. Typically. You can find a 50-year mortgage. I know someone that got a 50-year mortgage once because they were not very well off financially and they just needed the lowest payment possible. There are reasons to take a 15-year mortgage. There are reasons to take a 30-year mortgage. The most common is the 30-year mortgage. I would say if I had to just, wild random stab at it, I would say probably 90% of people get a 30-year mortgage, plus or minus 5%. And again, there are reasons that some people might get a 15-year mortgage, and we'll kind of go into the numbers of why that is. You can see it, but I'm not talking about it yet. 15-year mortgages tend to have a slightly lower interest rate. These are also from last semester. Thanks to coronavirus, these are more like a 3.25 and a 3.5 as far as I know. So let's update that. I might be off by 1/4%, so don't take that too serious. Also, these are based on your credit score. If you have a bad credit score, you're going to have 5 or 6% mortgages. If you've got an awesome credit score, you're dealing with these. So I like to approach these with good credit scores because you're much more likely to get a loan, especially right now. A lot of banks, because of them loaning out so much money due to the coronavirus, some of these banks are being a lot more strict about who they'll loan to. So if you have a bad credit score, they're going to go, or you got to pay 10% or something weird like that. Okay, so just laid out some scenarios here with numbers. If you got a 15-year, and I'm not going to redo the math, if you got a 15-year, 4.25%, $200,000 loan. So that doesn't say the value of the house is $200,000. That says you're getting a loan for $200,000. You also typically have to make a down payment to get your home. You have to put some money up front. So that way the bank gets some money out of this up front. The lawyers get some money out of this up front. And then you're reducing your actual mortgage payment. And that down payment can include fees and stuff. It's not just a down payment. I kind of sandwiched everything together there, not necessarily properly, but it all means the same. It's money you got to pay up front. So you end up borrowing 200 grand for 15 years at 4.25%. You're going to have a PMT means payment, a monthly payment of $1,500. And at the end of the 15 years, you will have paid the bank $70,900 in interest. How did I come up with that? Well, I have a calculator, I have a formula, but there's also a website, which is here, mortgagecalculator.org. If you just Google mortgage calculator, you can find that. mortgagecalculator.org. So home value, in fact, so home value, let's make it the same as the loan amount. The down payment, we're going to say we put 0 down, or you could change the home value to 210 and say the down payment was 10,000, whatever. Interest rate, we wanted 4.25. Loan term, we wanted 15 years. I'm going to zero out property tax, PMI, and home insurance. We're only talking about the mortgage. We are only talking about the loan. Now, you need to understand that when you have a mortgage, that's not all you're paying for. You also have to pay property tax every year. You have to pay home insurance every year, and those are proportional to the value of your home. So the more expensive your home, the more insurance you pay, the more property tax you pay. If you live in a waterfront area, you're going to pay significantly more insurance because of flooding potential. You might have a homeowners association you have to pay as well. So again, I'm ignoring all those aspects and only looking at the loan. So there's some advertisement stuff up here because I don't have ad block on this computer since it's not mine. Now if I hit calculate, look at this. Total monthly payment, $1,504, and they give cents, 56. What did I have it as? 1,504, I should have at least. I really, really hope. Yes, 1,505. So it was just rounded up to the nearest whole dollar, which makes sense because 56 would round up to a 5, 4 to 5. Then they tell you the total interest paid. So we don't even have to multiply the payments by 180 because you'd be paying that for 12 months a year, 15 years, so 180 payments. So you take 1,504.56 times 180 and you'll get some big number. Then you subtract your 200,000 and that's how much the bank gets paid over 15 years. 71 grand. 71 grand that the bank makes off of you on this 15-year loan. That's a lot of money. But they also let you borrow $200,000, which is a lot of money. So, I mean, opinion, I think they deserve to make some money off of that. If you're going to loan someone, 6 figures, I expect to make something off of that. So I think the bank should too. And honestly, this is a lot better of a scenario for us than it was 20, 30 years ago. When you're talking about home loans in the 70s and the 80s, you're talking 15% APR. Let's just change the interest rate from 4.25 to 15. So we're buying our house in 1979 now, a $200,000 house. Now, to be fair, the home values were way less then. But if that's what we were doing now, our payment goes from 1,500 to 2,800, and the interest goes from about 70,000 to 300,000. It quadruples. So we are living in an awesome time to have a mortgage because interest rates are extremely low. And that was a 4.25 loan that I did. I said realistically right now they're more like at 3.25 if you got a 15-year loan. Calculate. So really, that mortgage is only about 1,400 if you got it today, with total interest of 53,000. 53,000 versus the 70-some thousand, you're saving almost 20 grand in the long term. But that's 20 grand long-term savings, not 20 grand up front, not 20 grand at the end. It's over time. Okay, so that's our 15-year scenario that we have now studied extensively where these numbers came from. And again, there is a formula to be able to find the payment. Then you multiply the payment by 180 and subtract the $200,000 to get the interest. I skipped the formula. I'm not going to do that in this course. The 30-year loan, and again, using 4.75, just keeping these numbers intact, that loan, that payment ends up coming to 1043 rounded to the nearest whole. Let's show it in the website. So what did I say, 4.75, I think? Again, a little high for right now. Loan term, 30 years. We're not worried about start dates and all that garbage. Calculate. Look at this, 1043 with an interest of about 175,000. And we had over here, oops, wrong one. 1043 with interest, 175,586. Was it 586 up there as well? 586, good. Just making sure all my numbers matched. All you have to do is go to a website. In fact, if you just Google mortgage calculator, after some advertisements, they give you a much simplified version. So let's do 200 grand at 4.75 for 30 years. Look at that. 200,000. Look at that monthly payment. 1043. Look at that total cost of the mortgage, 375. Now they don't give you the interest. You have to subtract the 375 and the 200,000 to come up with the 75,586. So this is nice for quick calculations. That other website I showed you is awesome because it has other options like showing an amortization table. So let's actually show that now. Let's just show the monthly one. We don't need the charts. Let's hit that calculate button again. So an amortization schedule is how much you pay in interest and how much you pay in principal each month. So your actual interest is just simple interest on 1 month. So you take your 4.75%, you divide it by 12, and then you multiply that by your $200,000 balance to get the interest. Now we know what the payment was. We subtract the interest from the payment to get the principal. So if you're paying $791.67 in interest, that means the other $251.63 goes towards principal, and that gets subtracted from the balance. So the balance is just the $200,000 minus the $251. Then this $199,748 is our new balance. We use that to calculate the next interest. Because this is a little less than $200,000, the interest is a little less than last time. It goes down by about $1. It's not always $1. It's just in this scenario about $1. When the interest goes down $1, the principal payment goes up $1. So the balance drops about the same, but $1 more. So because this balance is lower, the interest is slightly lower, which means the principal payment is slightly higher. Principal is the money that you've paid towards the loan. So if you get a $200,000 loan and you have $10,000 in principal, that means if you sold your home for $200,000, in theory, you'd get 10 grand cash to keep. Now there's fees, you got to pay your real estate agents and such. So at the end of the day, that doesn't really happen exactly 10,000. But before that, if you had paid 10,000 in principal over a sum of time, that means if you sold it for the loan amount, you would get that principal back. So if your house costs, if you get a loan of 200,000, you have 190,000 in principal because your loan's almost paid off. If you sold it, that means you get 190,000 in cash, and you would just lose $10,000 on the sale, basically. So you'd have $190,000 to put towards another home. So what's fascinating about amortization schedules, I know I'm kind of jumping around, is that the interest is going down slowly over time. The principal payment is going up slowly over time. So April 2020 is when we started. Let's go to April 2030, 10 years in. So in April of 2030, we're looking at this row. 10 years in, we've only paid about $40,000 off on this loan. We're still paying more towards interest than principal, the 600 versus the 400. 20 years in, so let's go to April 2040. April. So 20 years in, we have now paid $100,000 off. So we have paid half the loan down, but we're 2/3 of the way through the loan. So this is not a linear relationship. You pay down this loan very, 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 very slowly at first, but it starts to pick up speed because there's a relationship to exponential growth. So in the last 10 years, you end up paying off half the loan. Let's look at 2045, April of 2045. So this is 5 years later, and that 5 years we paid down 45,000, which is more than we paid off in the first 10 years. And then in the last 5 years, we're going to pay off that remaining 55,000 to get our zero balance, and our home is now paid for. The government can't take it from us. That's actually a lie. They can if you don't pay your taxes. It's kind of annoying. You never really own your home. They can still take it from you if you don't pay your taxes. So pay your taxes. All right, so going back to what we were on before. And as a reminder, none of these included PMI, insurance, and taxes. Insurance and taxes probably going to run you $300 to $400 on your average price house in this area. Not on the waterfront, at least. PMI, maybe another $100 a month on average. PMI is insurance that a bank takes out against you, principal mortgage insurance, because they don't trust you at first. They don't trust you until you've paid down 20% of the value of the home. Once you've paid down 20% of the value, they now trust you. And it's honestly, they still don't trust you. It's just that, let's say all of a sudden you stop paying your mortgage, you bail, you move away, and now they're stuck holding this house, they're stuck holding the note. So what they have to do is really, really quickly put it on the market and sell it to cut their losses. Now, if you've only paid 2% of the house down, if they need to sell this house really quickly, they need to sell it on discount. Maybe 10, 15% discount, then they're going to lose money paying the real estate agents. They're going to lose about 20% roughly. So that puts them in the hole 18% on the value of this house because you cut and run. So what they do is they purchase insurance that they make you pay for. That way, in case you do run before that 20% is paid off, that they'll get that extra 20% back, but just that margin so that they'll be in the clear. But once you've paid 20% down, they're not really going to have that issue. They can sell it really, really quick. And even if they sell it at a 20% loss, they only have, at most 80% of the loan to pay off. So they'll walk out without losing money. Now, the way that interest payment stuff works, because you're paying this interest a lot more at first, you're really gaining that principal very slowly. It actually takes you about 10 years. If you start with no down payment, it takes you about 10 years to get to 20% principal for your PMI to go away. So that's roughly $100 a month for 10 years that you're going to pay for the bank's insurance, and you don't have a choice unless there are some doctors that can avoid PMI. There are some other different professions that can get loans that avoid PMI. I think a lot of the times first-time home buyers can get loans that avoid PMI. Things are a lot more readily available now with situations like that than they were 10, 20, 30 years ago, especially 20, 30 years ago. So if you can get a loan without PMI, go for that. I mean, unless it is a higher percentage APR, in which case, run the numbers first. The point of me giving you all this, especially the websites, is you can get an idea of what your mortgage is going to be before you go to the loan people, because when you go to the loan people, they have to run a credit check. And when you run credit checks, you get hits on your credit. Now, it's not a big hit. A lot of people like to misconstrue that it's a big hit. It's a small hit. But if you go do this a bunch of times, those little hits start adding up for for maybe 5 or 6 months. It goes away eventually. Oh boy. All right, so the 30-year mortgage, let's compare these numbers back to this stuff. Now my rants are done. We ended up paying about $1,000 a month for the 30-year mortgage, so about $450, $470 less each month, which sounds awesome. But look at the interest. You end up paying $175 grand. So what would you rather do? Would you rather have a loan that you only have to pay $71,000 in interest, or would you rather have a loan that you pay $175,000 in interest? In other words, if you take the 15-year loan, you have a long-term savings of 100 grand in this scenario. So the 15-year seems like the clear winner. Well, in my opinion, and my opinion has changed over time of this, that is not necessarily true for several reasons. First of all, if you take the 15-year loan, you're now paying an extra 500, just ballpark, extra $500 a month for this particular home. Maybe you don't have that extra $500. Maybe you can just squeak by on paying that $1,043 for the mortgage, and then the other like $300, $400, $500 for PMI, insurance, and taxes. So maybe you can't afford the 15-year mortgage. Guess what? Don't get the 15-year mortgage, because you're going to default on your loan and you're going to lose it. So it's a matter of having the capital or having the ability to not spend one or the other to be able to take the shorter term loan to get that interest savings. But even then, there is nothing definitive that says the 15-year loan is better than the 30-year loan, because what have we been talking about previously before this? We did a whole bunch of examples with Bob putting money away for a retirement. So if you're someone who just hates debt and needs to get your debt gone immediately, and I completely understand that mindset, debt feels terrible, but there is good debt, and I'm suggesting that mortgage is a good debt. So if you are a person who hates debt, you get the 15-year loan, you make sure you have a home that you can afford that payment, and you end up saving yourself, maybe 50, maybe 80, maybe $100,000 in interest long term. And that sounds awesome. But if you actually consider all financial aspects, if you consider, hey, I could be putting my money into a retirement plan. Now, these mortgages right now are running 3%, 4%, 5%, depending on your credit. Retirement plans, long-term, over 30, 40, 50 years, on average, basing on the S&P 500 numbers, on average get you 7%. When you do your own kind of investments, when you do more research and find better bundles to put your money in, maybe you can get 8, 9, 10%. The basic idea is, if you can put away money into a higher percent than what your debt is, you should be doing that instead. So if I can get a retirement plan that I believe will get me 10% every year for all my life, and my mortgage is only going to run me 4%, I should actually take the longer mortgage, and instead of using that extra money to pay it towards the 15-year loan, I can take that extra money and put it towards my 10% retirement plan. And even though I'll pay more interest to the bank, I will net more interest in my retirement plan, and it's not a small number either. So that's what this stuff goes on to talk about. And we have like 3 or 4 minutes, so this is going to be quick. I'll show you the website super quick. Annuity calculator on calculator.net. This is one of my favorite things. I have changed people's lives with this website. And I don't mean to exaggerate that, but I really have, because this shows you just how absolutely rich in theory you could be if you start retiring early. And we already did this with Excel, but this gives you just a much simpler way to play with the numbers. So what were our numbers? So let's say, what if you invested that extra $462 each month in a retirement account earning 7% compounded monthly? So I'm just going with the safer S&P 500 assumed average. So we're assuming we could have afforded the 15-year mortgage, but we're going to take the 30-year mortgage. Now, we're only paying $1,043 a month to the mortgage, but I know I could have afforded the 15-year, so why not, instead of taking that money and buying a new boat or a fancier car or lots of vacations or whatever? No, vacations are awesome, love vacations, but maybe you just hold off on them. I don't know, not suggesting it necessarily, you do what you want, but I'm telling you, instead of taking that extra money and putting it towards, quote, fun stuff, you put it towards investing in yourself, so maybe you can retire early or retire at all. So that was a difference of $462 between these two payments. So we'll make our 1043 payment to the bank on the 30-year mortgage, but we'll take the extra $462 and we'll put it into a fund that gets us what we assume to be 7% long-term. And if you deposit $462 monthly for 30 years at 7% interest, you're going to end up getting this amount, $543,000 and some change, which ends up being $377,000 and some change in interest. So by taking the 30-year mortgage instead of the 15-year mortgage and pairing that with a solid retirement plan, taking the extra cash again, if we had that cash, taking that extra cash and putting into retirement, that means our retirement plan has almost 400 grand of free money in it. Now, this is money that we would not see if we had just taken the 15-year mortgage. So yeah, you end up paying an extra $100,000 to the bank, but then you have an extra $400,000 in interest, netting you an extra $300,000 total, which if you invest in what we call a Roth IRA, every single penny of that could be free. Tax-free, not free, tax-free. Is that the only option you have, though? No. So what someone else could do, there's another scenario, is someone will say, all right, I'm just going to get the 15-year loan because I hate debt. I hate debt. I come from the land of debt. My parents, they went under, something like that. So this theoretical person, so we got to get the mortgage paid off quicker. So we take the 15-year instead of the 30. We know that we can pay the $1,505 every month. So what we do is we take the first 15 years and we pay off the mortgage. Now, year 16, year 17, year 18, we have no mortgage. We're not paying $1,500 a month to a bank, which means we now have access to another $1,500 every month that we didn't. So you have 15 years of access where you would have been paying the 30-year mortgage, but now you've got $1,500 a month to throw into retirement planning. So now, instead of putting $462 a month away for 30 years, we're going to put $1,505 away for 15 years, the entire 15-year mortgage payment for that last half of what someone else would be paying for their mortgage. Now, when you do that, if you use that calculator, which I'll do in just a minute, I'll show you one of the calculations. It turns out that your retirement plan goes up to $471,000 roughly, meaning you've received $200,000 in interest for free. If you multiply 1,505 times 12 times 15 to get the total you put in, that would be the difference of those two things. So 470 minus whatever that number was gives you your 200,000, roughly 270,000 you put in. So that's still awesome. There's nothing wrong with this scenario. A person who gets a 15-year mortgage, pays it off in 15 years, and then takes that entire payment and invests it for 15 years, they still get $200,000 for free, which means they end up netting $130,000 from the whole experience because they pay the bank $70 and they get $200 for free. So that's still awesome. But wouldn't you rather have $377,000 for free instead of $200,000 for free, especially after subtracting the interest? This nets you $130,000 after you subtract the bank's interest, whereas this one nets you about $200,000. I would rather net $200,000 for free. So I'd rather take the 30-year mortgage in that scenario in theory. But again, that's not telling you what to do. That's not advice, it's education. Like I said, a lot of us, we're never going to have the ability to pay for that 15-year mortgage. So we stick with the 30 and we invest when we can. But if you look at two plans for the house you want, and you know that you could have paid for that 15-year mortgage, if you wanted to be financially sound later, you take the difference of that payment, you invest it for 30 years, and you end up rich. So I think that the 30-year scenario is better for two reasons. You net more money, and this is again assuming the market trends at 7% average per year. Then also, let's say one of those months you have to have a surgery or something. You got a whole bunch of doctor bills, or whatever. It could be anything. Your car breaks down. You got to buy a new car. You got to start having a car payment for a while. Whatever. If you take the 30-year mortgage, you don't have to dump the 462 into a retirement plan. That's optional. So you can skip it for a few months, or maybe just put 100 this month, or 250 this month, or whatever. But if you take that 15-year mortgage, you're responsible for that $1,500 every single month. And if you've got 1 month or 2 months that's tight, you're going to miss a payment. You're going to end up paying a fee for that. You miss too many payments, they take your home from you. But again, ultimately, you have to decide whether you want the risk or not. Again, a lot of people are anti-debt, which I completely get. So they go for the 15-year mortgage when they can afford it. It's honestly not a lot of people, but the people that think they want it go for that. But then you have a lot of people that want the most money possible, so they take the 30-year option, they invest extra, and they retire rich. Remember, all of this is speculative, educational purposes, not advice. So let's finish with actually putting in those numbers. $462 a month for 30 years. Let's just do that one in that website. I'm going to hold you for an extra minute or two. So starting is nothing. Annual edition, nothing. Monthly edition, $462. Annual interest rate of 7%, and we're doing this for 30 years. Calculate. Total balance, $543,000. How much we put in, $166,000. How much we get for free, $377,000. It even gives you graphs. It gives you pie charts of how much is principal and interest. I love the pie chart because the principal is a smaller slice than the interest. It says we put in this little bit and we get this big chunk for free. Now, if you're not retiring 30 years later, what you could do is then take your mortgage payment and put that whole $1,505 in this. So now let's say you start with $543,000, $341, $543,341. Now we're going to add a monthly addition of $1,505. So 30 years have passed. We netted this $543,000. But let's say we're 55 and we're going to retire at 65. So let's do this for another 10 years. So we got $500,000. Now we're adding an entire 15-year mortgage payment to it. Let's see what we end up with. Positive annual. I thought I typed 0. There we go. So if for that next 10 years, we deposited our entire mortgage payment into a retirement plan, which we would not be able to do that completely tax-free, at least not in our account, not right now into an IRA. You'd have to split it between IRAs and 401ks. We'll get into some of that next time. $1.3 million. $600,000 in interest for free. Now, because you start dumping so much more of your own money at the end, that principal to interest ratio does shoot up, which is not a problem. But the money you put in at the beginning gets you a lot more interest than the money you put in at the end because of compounding effect. Now, maybe you say, I don't want to do this. I don't want to continue to put my entire mortgage. I want to have some fun. I want to enjoy my life, and I get that. So maybe you just keep putting in the difference of the two. So let's see how much we'd have now instead. So kind of an intermediate. You still get 1.1 million. Also, the principal interest is thrown off because of the starting balance. Actually, this breakdown is completely trash, honestly, because a lot of this money was free money. So let's instead just start with 0 and say we did the 462 for 40 years. So 30 years, we were still paying down the mortgage, but in the last 10 years, we kept adding in that amount. We still have $1,000 to play with and have fun those last 10 years. That is not a bad thing. That's a much better breakdown. You can see that only 20% was our money, 80% was free money. And again, that would be completely tax-free if thrown into a Roth IRA. So you've got $920,000 tax-free in a Roth IRA doing this. Something that can make or break you. So we'll call it a day there. Have a good weekend. Get some work done, get some studying done. Go ahead and start looking over the midterm material again. Like I said, I will have the last quote half of the material ready by Monday morning. If I get it prepared anytime sooner, I'll shoot you an email and let you know that it's available if I can get it up Saturday or Sunday, because that's when I'm going to be working on them. Make sure you know all the due dates and everything. Nope, not that one. This one. There we go. There it is, one last time. Besides that, have a good day. We'll see you on Monday.